Well, and now we'll talk about the mechanical properties at room temperature. And well, more or less the behavior of these ceramic, of these mask faces are like ceramics, but I would like that at least you have in mind that the structure of the mask faces can do something like that when you measure the mechanical properties. They are not brittle. I mean, they can be bended or even do this kind of a structure. They resist a lot, and well, this is the reason is the king band that is called is one of the main characteristics of these mask faces, and then of course at the end they are broken, but they can resist a lot, and the mechanical properties for that is totally different in comparison with, for example, with the MX ceramics, the titanium carbide. If we are talking about that, it's impossible to do that one obviously with a ceramic or bending. Okay. Well, but mention this is also important that, however, they are soft. I mean, the hardness of the material. Well, here for that I put that. Obviously, I will not go in detail, but the hardness it's low. Okay. Just to mention, obviously, I will not talk about that, but the important thing is that obviously, and in other materials, it depends about the grind size. If you want, obviously, to promote this kind of mechanism, you need to do a long thermal treatment, or at least that the grains grow enough to have these really nice nanoplatelet structures, okay, that are long. If you keep your grind size really small, of course, they cannot be something like that, okay. But okay, on the other hand, of course, if you have this coarse grain size, the sample are weaker, okay. And the other properties are more or less like ceramic. Let's say in compression are quite good, but are poor in tension. This is obvious. I mean, with that we cannot do anything, especially at room temperature. And here, just to show you, well, some difference between a really thin or fine grain material. Obviously, what this L-Ragi work with Barsom, they work together, or this coarse grain and this elongate grain. And well, I think their values are somewhere in this table, yeah, this figure, and how they measure determine values. Of course, they can tailor the properties as a function of microstructure, like in the ceramics, I mean, or even in the metals. And here, this is critical, depend of your grain size. From that, at least to keep in mind, well, it is the density as a function of flexural strength. If you need or you want a really high flexural strength to be a ceramic, you should go in the order in the finest microstructures, like that. If for other properties you need it, but then you will lose flexural strength. Okay, you are here in the order, for example, to compare this material with that one, just here 10 microns of mean grain size, or here 25, and it's obvious here like a gap. Okay, if you need larger flexural strength, you should go for the low grain sizes. Okay, and here one of the samples of they are layered structures. The crack fractures can be stopped. Even the fracture toughness, as I told you, has been measured up to 20, and is for this reason. I mean, you can deflate all the time the crack readily. Okay, here I think it's so better how it's deflected when the crankcase it moves, and then you start to reduce the energy. Okay, you can highly orient it also your materials, and then the crack is deflected. Okay, well, more data, but in summarize, this is maybe that you should take in mind that are relative soft. It's not like ceramics that they are always hard. These mask faces are soft. Okay, they are not more than 8 gigapascal of hardness. Okay, for some properties are good, for example, for the machining, but for others are worse. Okay, and just here some informations again, like the ceramics depends again your. If it's coarse grains or the fine grains, you can more or less tailor the properties, but it's important to remark that the weaker hardness, or hardness in general, it's quite low. Okay? Even with that, depends of the grain size. This is obvious, like in all the materials. Okay. And here one example. Well, maybe the resolution is not the best one, but this is for this kill band that when you do an indentation, the typical in ceramics, I don't know if I have a picture. I don't know if all of you know, but you do your indentation and there are normally 4 cracks, okay, because your material cannot survive, let's say, against this crack. The fracture toughness is quite low and they have not mechanisms to protect these cracks. But these mag faces are totally different. When you produce or you indent your bigger tip, there is an area that is obviously deformed, but then there are not cracks, because that you produce when you introduce your tip is some delamination and some kit buds surrounded here, like here, and then they absorb all the energy, okay? You absorb the energy of the indentation, and then there are no cracks. Then the material can really survive. You absorb all the mechanisms in the vicinity of your indentation, and this is a quite interesting response of the material that should be great if there are more studies at high temperature. But okay, fortunately, there are not many. But this lack of cracks, it's a really good result. Okay, and well, here more images, in that case TEM images, about, like always, probably, yeah, exactly, like always in this titanium silicon carbide, but there are more than 70 max faces, and who knows what is the other, if they have also other mechanisms or some band. But well, here just to show you this skin band, that this move or this delamination that absorbs all the energy. Okay, and fracture toughness, the main problem of the ceramics, as always. Well, the values normally in mag faces can be tailored between 5 and 20. That, to be honest, is a quite respectable values in comparison with other ceramics. Of course, it's impossible to achieve these values. Even in maybe silicon nitride or other materials has a really good response, but not like that. You want to go these values, obviously you should go for the CMCs. Yeah? Just values for what is the literature, but yeah, you see 18 even in other phases, or yeah, 16s, depend the grain size obviously, but different values. Okay, and again, we mentioned before that it's better for the flexural strength to have low grain sizes, but for example for fracture toughness, of course you need this kind of king banks, and they are promoted with larger grain size, and here they improve the fracture toughness, like in other ceramics. If you have larger grains, obviously your fracture toughness will be higher. Okay, and here, well, there are a few examples about that, but as you see, we are talking about really resistance materials. And just, well, here example about this fracture toughness as function of flexural strength, because it's a compromise between the grain size. Well, here a lot of ceramics, quite good, even some mag faces. Silicon nitride, that I told you, the fracture toughness is quite good in combination with the flexural strength. Obviously the sialons here is not shown, but it's a mag face, and here sorry, if you texture even the max faces, and now the idea, obviously, if we are in the first stage of to develop new max faces, even there are not all of them discovered, the tendency is maybe going in that direction, that the fracture toughness is quite high. And then there are really promising materials. Unfortunately, there are not many research, at least now, in that. And well, here now another plot to have idea where we can locate the materials. This fracture stress a function of fracture toughness. Again, always that if in ceramics we talk about fracture toughness, normally silicon nitride is one of the best materials, and then there are here, or also here, if you put seeds of this silicon nitride to have a really elongate beta faces. But okay, we are talking that we can even improve these values. Okay, and why is the reason? By this crack deflection that I barely introduced you at the beginning. I mean, the crack is not just one crack that continue like in your material, like if nothing happened. Here is all the time. Whoa, it's deflecting and taking these layer structures, okay, and moving. And also, for example, here you see one of these mass phase, one grain that is doing some mechanics, okay. Well, here more detail about some part here or here probably, okay, about how they deflect, and then you start to lose your energy. But of course, and this is important, if you want to control or to have high fracture toughness, you should control the grain size. That should be the highest as possible, only if you have coarse grains, okay. And here, sorry, more examples how the crack, in the direction going in that one, how this delamination process, or here, that one, how they are bent. Fortunately, the resolution is not as good as here, but you see here there's delamination, or here this skin bank that are moving, and of course this one is totally impossible to see in a ceramic materials, and that's the reason why if the crack is deflected and delaminated the matrix, of course you absorb a lot of energy, okay? But well, anyway, this is room temperature. We'll see now at high temperature, okay? Another important thing in ceramics always the damage tolerance. This is also the problem of the ceramics. If you have a ceramics and fall down, it breaks, but in math phases some of them is not like that, okay? To measure normally the damage tolerance, it's not in your samples. Normally that you do is some indentation and measure what is the tensile response of your material, and when they breaks. But here, as you see, they can perfectly keep, or well, maybe this one not so much, but they are totally constant in the flexural strength with the number of indentation. And here one example that for me is quite interested in this titanium aluminum carbide that also present an excellent oxidation resistance. If you hit with a hammer, instead break it, only it's like a metal response. Of course, you produce something in your material like a deflection because they are soft, but they are not cracked. I mean, because all the energy are absorbed by these key banks and crack deflection, and then you can hit it, and you will not break the material. I mean, it's like a metal. This is incredible. I took from the book, but this sample was repeated and repeated, hit it with a hammer, and you just can do like that. Maybe you think that this is not quite interesting, but to be honest, if you do that one in a ceramic, of course forget from the first impact. Okay. And well, here the thermal shock resistance. Of course, as always, if we are talking of high temperature, the thermal shock is quite important. Okay. Then, well, that should be obviously measured. And well, here, for example, obviously depend of your material. Here, for example, a couple of examples totally different. If you have a fine grain, coarse grains, they are different, but it is important to mention. For example, if it's fine grain at some point and you quench in temperature, well, maybe you don't know about that. That here that you do is you heat your material, for example, 800 degrees, and you remove from the furnace and throw it directly in water. Okay, and then this is called quenching. Okay, and then you measure the properties and you see if they are keep it or your material is full of micro cracks or other cracks, and then your material fails. Okay, and well, as you see here, well, it depends of course of your grain size, but they can, for example, in that case survive several quenchings at really high temperatures. Okay, and it's important to see, for example, this increase also at really high temperature. It's like that, and after increase, or here, and this is by this self-healing effect that we have talked. Even they respond better at really high temperatures than at intermediate temperatures, because at really high temperatures that you form is the feeling of these micro cracks, and then your material at the end will have better response. Okay, and it's quite interesting, but unfortunately there are not many works on that. And well, now the mechanical properties, but at high temperature. Okay, because of course this is the idea, and the good part of these mass phases is that even they are more interested at high temperature that I show you now that at room temperature, because there are not many materials that keep the properties at high temperatures. Okay, and here that we can see, or I want to plot that even some of them well, obviously at brittle, but at some point of the temperature has a response like a plastic transition, okay, that is called BPTT. And this is quite interesting in some materials. In the next slide is about that. They don't fail like abruptly, like a catastrophic failure. It's going more in a direction in a plastic deformation, okay? But again, all the studies are based on this material, but the other phases practically we don't know anything. For example, here, and I want to mention, not everything is good, but well, here, for example, the fracture toughness has a drop, but to be honest, a really high temperature, even higher than 1000 degree. But this is like the inverse. It passes to ductile to brittle material. Okay. And here, well, I think during these days I saw you a few slides about the stress as a function of the strains. Well, all of you, I think, are engineers and probably even more than me. But that is important to remark here is, well, first that it was to a relative high temperature in air, and well, depend the stress that we are putting, they can react more or less like a conventional ceramic, but also at some point, depend of the strains, if we reduce the stress, it belongs more or like that one, like in a brittle, in a ductile behavior that is quite interested for a ceramic for some short application. It's a plastic response, and this is quite interesting. Okay, and here some of the reason how it deforms and the compression here in that case, and it's again by this layer structure and how the energy can absorb or even the crash can be deflected. Okay, this is more in detail. Well, I'm going to put here the next slide is even more clear. This is the other most studied phase, this titanium aluminum carbide, when it's the fracture surfaces under tension at 1100 degrees. Okay, and this sample at the end fails at 3 hours. Okay, but well, the strain failure is 16, that is quite hard. And here you can see this layer structure of the material that is clear, or even here this picture, I really like it, how the grains are bending to obtain this. Is totally impossible in other ceramics. Okay, and this is for this layer structure. And here, well, obviously, if we talk about temperature, creep is totally critical. Obviously, if we want to use this material, this is not the case like the ultra high temperature ceramics that is for a few minutes or few seconds. This one is like a structural material, or the idea to use it. Creep is totally critical, and obviously depends obviously in time and stress and in the temperature. And well, here is a few examples how is this evolution also as a function of the coarser grain or the fine grains or different materials. Okay, how is, for example, at 1200 it's quite good, at 1300 that one start to be lower. It's just different values. Okay, I don't want to bother you with that. And also, well, the compressive stress, how they react here. It's not a catastrophic failure. It going better, or also at higher temperature they start to develop this one. It's ductile mechanisms that are much better than even at room temperature. I think it's quite amazing. More work has been done in high temperature, but it's quite important. Here, well, about the compressive stress, for example, of this chromium, about the effect of temperature. We are talking here at this intermediate temperature, and they keep already good values. Okay, for example, ultra high temperature ceramics, I think they keep at this temperature even better values, but other properties are much lower than these max phases, present really good values. And the flexural strength, again at room temperature the catastrophic failure, but if you increase the temperature, even the response depend for the application, but could be better. Here is ductile, your material doesn't break directly. Okay, more example also, if you do some solid state, I mean incorporate some elements by solid solution, in your structure, different response, but always at too high temperature would result. Normally the threshold is around 1200, 1300, and for that temperature they respond quite well. Well, that was the idea, to have just an overview. I don't want to bother you with many things, but at least you have heard about Mac faces that probably you never heard. And that's all. Thank you for your attention. And what time for questions if you have it? If not, tomorrow 9:30, last day, and yeah, that's all. Thank you for coming. Yeah, bye.